Okay, 5.3, partial fractions. Two learning targets here. First one, find the form of the partial fraction, and then the second one, find the partial fraction decomposition. And you'll understand what that means when we get to the end of this lesson. So a little bit of background to begin with. In Math 1010, you were taught how to add two rational expressions together. And honestly, you've been taught how to add fractions together by getting common denominator. So this one we need to be multiplied by x minus 1 over x minus 1. This fraction would need to be multiplied by x plus 2 over x plus 2. So then what happens here in the numerator if you distribute is you get 4x plus 8. And there if you distribute you get 3x minus 3. And then if you combine those numerators, you get 7x plus 5, and your common denominator stays the same, x plus 2 over x minus 1. This is what you were taught in Math 1010. To take two separate fractions, or in this case rational expressions, and add them together into one single rational expression. So in essence, you went in this direction. What we're learning today in this lesson is how to reverse that process. So you're going to start with a single rational expression, and by performing what's called partial fraction decomposition, you are going to determine the partial fractions. So these are what are called the partial fractions of this rational expression. The reason for doing this, you wouldn't really see unless you are going to take a calculus course. One of the primary reasons for partial fraction decomposition is in integral calculus. It's much easier to find the antiderivative of separate partial fractions than it is of a combined rational expression like this. But unfortunately, you would need calculus skills in order to make that happen. So all we do in Math 1050 is practice the skill of finding the partial fractions. Beyond that, we don't really do anything with them. The reason it's in Chapter 5, it does possibly seem a little out of place. See, Chapter 5 deals with systems of equations. And you're thinking, well, what does this have to do with systems of equations? There is a way to find partial fractions that involves using a system of equations, and that's why it's in Chapter 5. I'm going to show you some techniques where you do not need to use systems of equations to solve for the partial fractions. Now, learning target 1 is called just finding the form of the partial fractions. And it consists in one of several different ways. The form of the partial fractions depends on what you have in the denominator. So let me repeat that. The form of the partial fractions depends on what you have in the denominator. If your denominator is distinct linear factors, distinct means they appear only once. So x plus 1 appears only once, it's distinct. X minus 3 appears only once, it's distinct. Linear means that each factor, the highest exponent inside the factor, is 1. So this is, or it's a first degree polynomial. So x to the first plus 1 and x to the first minus 3. So those are linear factors. If your denominator is distinct linear factors, then this is how you find the form of the partial fractions. First of all, you're going to have the same number of partial fractions as you have factors. So in this case, if you have two factors, you're going to have two partial fractions. And each one is going to have one of the denominators. So one of them is going to have a denominator of x plus 1. The other one is going to have a denominator of x minus 3. And then the numerator has to be 1 degree less than the denominator. So let me clarify that. This denominator here is a degree 1 polynomial. Same thing with this one. X minus 3 is a degree 1 polynomial. So your numerator needs to be 1 degree less than that, which is degree 0. And I think I might have mentioned this briefly in another lesson, but something that's considered degree 0 is just a constant, like 10 or 15 or -2. A constant with no variable is considered degree 0. So your numerators in this case are just going to be constants. I'm going to call one of them A and one of them B. And the process of finding the actual partial fractions involves solving for A and B. If all you're asked for is the form of the partial fractions, then this is what they look like. We don't need to solve for A or B if the textbook or on an exam it just asks for the form of the partial fractions. This would be it. Two partial fractions, each of them have one of the denominators, and then the numerators are constants, in this case A and B. So this one here, since we see 3 distinct linear factors, we're going to have 3 partial fractions. Each one of the partial fractions has one of the factors in the denominator. And then, again, since the numerator has to be at 1 degree less, it's going to be a degree 0, or constants, so you can use A, B, and C representing the constants, which we're going to learn how to solve for here in just a minute, but if we're just finding the form of the partial fractions, that's how you would leave it. Now, the second case is if you have what are called repeated linear factors in the denominator. Repeated obviously means that the factor appears more than once, so x minus 2 here appears twice. So the form of the partial fractions are going to look slightly different. It is still true that the number of partial fractions is equal to the number of factors. And even though x minus 2 appears twice, it's still 2 factors. So you're going to have 2 partial fractions. The difference here is when you have repeated factors, every time it repeats, you have to increase the exponent. So the first time you write it, it's just simply the factor x minus 2. The second time you write it, it's x minus 2 squared. If this had repeated a third time, you would write one more partial fraction with x minus 2 to the third power. Now, it is still true that the numerator needs to be 1 degree less than the actual degree of the factor itself. So this factor is still a degree 1 polynomial, so the numerator would be a degree 0 or just a constant. And same thing here, this factor is still a degree 1 factor. I know it's repeated here twice with this exponent, but the factor itself is degree 1, and so the numerator just needs to be a constant of degree 0. So this would be the form of the partial fractions when you have repeated linear factors. So another example here to look at, we have x plus 1 repeated 3 times, which means we're going to have 3 partial fractions. And then since x plus 1 is the repeated factor, each time it repeats, you have to increase the exponent by 1. Until finally the exponent here needs to match the number of times it repeats. So if it repeats 3 times, you continue to increase the exponent up to an exponent of 3. And then the numerators are just going to be constants, a, b, and c. Now, it's actually more common to combine what we've just done, meaning repeated linear factors and distinct linear factors. It's more common to have a combination of that. See here, x minus 2 is a distinct linear factor because it appears only once, but x plus 1 is repeated since it appears twice. there are still three factors. X minus 2 and x plus 1 appears twice. So there's three factors, meaning there's going to be three partial fractions. X minus 2 only appears once. But x plus 1 is the repeated one. So the first time you write it, it's repeated once. The second time you write it, it has to have an exponent of 2. And then the numerators are going to be degree 0 or constants. So that would be the form of the partial fractions for this rational expression. So again, read the directions on your homework carefully. If all it is requiring you to do is write the form of the partial fractions, then this is all that's required. You don't need to solve for the values of a, b, and c. That's the next learning target, which is partial fraction decomposition. Now there's one third case that we need to look at. It's when you have what's called an irreducible quadratic factor. Irreducible quadratic factors in the denominator. Irreducible quadratic factor means that you have a quadratic expression that does not factor. X squared plus x plus 1 does not factor into linear factors like x minus 2 or x plus 5. X squared plus x plus 1 is irreducible or non-factorable. And then we have a distinct linear factor here, and it's actually common to have irreducible quadratic factors in combination with some of the others that we've talked about thus far. So x minus 2 is a factor, and x squared plus x plus 1 is an irreducible quadratic factor. So there are two factors, which means we're going to have two partial fractions. And each one is going to have one of the factors of the denominator. So x minus 2, and then x squared plus x plus 1. There. Now, this factor, x minus 2, is a degree 1 polynomial, so its numerator needs to be 1 degree less, so that's just a constant, a. This one, however, since it's irreducible quadratic, this is degree 2. So the numerator needs to be 1 degree less than that, which is a degree 1 polynomial. And now let me repeat that. Since this is irreducible, this is considered to be a degree 2 polynomial factor. So then the numerator needs to be 1 degree less than that, which is degree 1. A degree 1 is a linear factor in the form mx plus b. So what it would look like, since I've already used a, I'm going to switch to the next available letter, which is b, and call it bx plus c. This constitutes a degree 1 polynomial, and that's 1 less degree than degree 2. So if you have an irreducible quadratic factor in the denominator, then in the numerator the form of the partial fraction is a degree 1 polynomial. And I chose to use b and c because over here I had already used a. And this would be the form of the partial fraction. So another one to look at here. I've got a distinct linear factor, I've got a repeated linear factor, and then I've got an irreducible quadratic factor. So I've got 1, 2, 3, 4 factors in the denominator here, which means we're going to have 4 partial fractions. And each denominator of the partial fractions is going to be one of these factors here. So x plus 1 is the distinct linear factor, and then x minus 2 is the repeated factor, so it needs to repeat following the same procedure that we saw just a few minutes ago. And then x squared plus 7x plus 2 is the irreducible quadratic factor. Now all of these linear factors, their numerators are just going to be constants. I'm going to call it a, b, and c. But this irreducible quadratic factor, the numerator has to be a linear expression. And since I've already used a, b, and c, I'm going to use dx plus e. And this would be the form of the partial fractions for this rational expression. The next learning target would be learning a process to help us find the actual values of a, b, c, d, and e in that case, or a, b, and c. So let's take a look at that now. This is called finding the partial fraction decomposition. Matter of fact, let me go ahead and make a slight change here just to illustrate a point. It may happen, matter of fact, it's likely to happen that your denominator is not in factored form to begin with. And what I suppose maybe they're trying to confuse you with is this case here where you start with an irreducible quadratic factor. So always check, this actually is not irreducible, it's factorable. You can factor that into two factors, x plus 3 and x minus 2. So now you recognize, okay, we've got two distinct linear factors. So step one of partial fraction decomposition is actually what we just did. Step one is to find the form of the partial fractions. So since we have two distinct factors in the denominator, we're going to have two partial fractions. So that would be the form of the partial fractions. Now step two, and I've mentioned this idea before in earlier videos, nobody likes to solve equations that involves fractions. This is one big nasty equation that has lots of fractions. One way you can simplify this before solving is to get rid of the fractions. And the best way to get rid of fractions is to multiply the whole equation by the lowest common denominator. So if all of these fractions were to have the same denominator, it would be x plus 3, x minus 2. See, this one would need to be multiplied by x minus 2 over x minus 2. This one would need to be multiplied by x plus 3 over x plus 3. So eventually all three pieces to this equation would have a denominator of x plus 3 times x minus 2. So that is our common denominator. So I'm going to multiply the whole thing by the common denominator, x plus 3 times x minus 2. And then what we do is distribute that common denominator to all three pieces. So if the common denominator multiplies all the way over here, the x plus 3, x minus 2 would just cancel out, leaving the 6x minus 2 in the numerator. So 6x minus 2 with no denominator. Now when the LCD here multiplies to that partial fraction, just the x plus 3's are going to cancel, so then a would multiply with the x minus 2. So a multiplies with x minus 2. Now when the LCD multiplies to this partial fraction, just the x minus 2's cancel in this point, so b multiplies with x plus 3. Now, we have an equation with no denominators. It's an equation with no fractions, but it's an equation that has the same solutions as what we started with. Just a little bit easier to solve. Now at this point, if you're following along in the textbook, they introduce a way to proceed that does involve systems of equations, which is why this is in Chapter 5. I'm going to show you a way that I believe is a little quicker and easier that does not involve systems of equations. What we're solving for is not x. We're solving for a and b. Now that does present a problem though. We only have one equation with two variables, a and b. So if I could somehow get rid of part of this, for example, if a disappeared, or if this piece of the equation disappeared, all that I would be left solving for is b. And this is based off a previous statement that I just said, we're not solving for x. If that's the case, it doesn't matter what x equals. We can allow x to equal any value. If you choose wisely, however, in this case, if we let x equal 2, the reason I chose 2 in particular is when I plug a 2 in there, 2 minus 2 is 0, and then 0 times a is 0, which eliminates that whole piece of the equation, allowing me to solve for b. So some textbooks call this technique choosing convenient values. X equals 2 would be a convenient value because it eliminates part of the equation. So if we let x equal 2, that means all of the variables, or not all of the, all of the x variables rather, take on that value of 2. So here 6 times 2 is 12. 12 minus 2 is 10. And then here 2 minus 2 is 0, and 0 times a is 0. So that part goes away. And then here 2 plus 3 is 5. 5 times b is 5b. Divide by 5. So b equals 2. Now we repeat the process because we've solved for one of the variables, but we haven't solved for the other one, a. So now we choose another convenient value that this time would cancel b. If I can cancel b, that will allow me to solve for a. So I notice right here that b is attached to a factor of x plus 3. If I can make this factor 0, then 0 times b would be 0, which would allow me to solve for a. So the convenient value there would be to let x equal negative 3, because if I plug that in there, negative 3 plus 3 is 0. But this means that all three x values are going to take on that value of negative 3. So 6 times negative 3 is negative 18, minus 2 is negative 20. And then negative 3 minus 2 is negative 5 times a is negative 5a. And then negative 3 plus 3 is 0. 0 times b is 0. So b does not appear in this equation. Divide both sides by negative 5, and we get a is equal to 4. So now that we have the values of a and b, we can complete the partial fractions. See, here all we had was the form of the partial fractions. We did not know the value of a or b. Now we do. So the actual partial fractions would be 4 over x plus 3 instead of a over x plus 3, and then 2 over x minus 2. These are the partial fractions. And we can check if we were to add these two together, like what I showed you at the very beginning of this lesson with that background information. If these two expressions were added together, what you would end up with is this expression right here. Let me just show you that real quick. In order to add these together, you need to have a common denominator. So what I would need is to multiply this by x plus 3 over x plus 3. This one would need to be multiplied by x minus 2 over x minus 2. And then when we distribute there, I'm going to get 4x minus 8. If you distribute here, you're going to get 2x plus 6. If you combine those terms in the numerator, you're going to get 6x minus 2, and then your common denominator is x minus 2 over x plus 3, which is exactly what we started with. So that shows that we have the correct partial fractions. So that's finding the partial fractions, or partial fraction decomposition. That was with a case of distinct linear factors. If we have a case here where we have a combination of a distinct linear factor and a repeated factor, the process is similar, It's still step one, which is find the form of the partial fraction. Since we have three factors, we're going to have three partial fractions, x plus 1, and since x minus 2 is the repeated factor, it's x minus 2 and then x minus 2 squared with denominators of a, b, and c. So there's step one, write the form of the partial fraction. Step two is to multiply the whole equation by the lowest common denominator. That's always going to be the denominator that you start with in factored form. So that's going to be our lowest common denominator. That's what we need to multiply by. X plus 1 times x minus 2 squared. Now when that LCD multiplies all the way to here, the whole denominators cancel out. So you're just left with the numerator, 5x squared minus 12x plus 1. Now when the LCD multiplies to the a partial fraction, the x plus 1's cancel, so a multiplies with x minus 2 squared. Now when the lowest common denominator multiplies the b partial fraction, this x minus 2 only cancels with one of the x minus 2's. So then b multiplies with x plus 1 and one of the x minus 2's. Now when the LCD multiplies here, the x minus 2 squared cancels completely out with that x minus 2 squared, so c multiplies just with x plus 1. Okay, now we're to the step where we choose convenient values, and I want to choose a convenient value this time that's going to wipe out two pieces of the equation, leaving only one piece to solve for. So you might have to think a little bit harder, but if you notice here, if x equals 2, then that's going to cancel both of these pieces, allowing me to solve for c. So my first convenient value would be to let x equal 2. And then you plug a 2 in for all the x's. So here, 2 squared is 4. 4 times 5 is 20. 20 minus 12 times 2 is 20 minus 24, that's negative 4. Negative 4 plus 1 is negative 3. And then a 2 here, 2 minus 2 is 0, so a is gone. Here, 2 minus 2 is 0. 0 times that is 0, so b is gone. Here, 2 plus 1 is 3. 3 times c is 3c. So c equals negative 1. So we found one of the values. Got to choose another convenient value, and again, the convenient value has to eliminate two pieces of this equation. So another one I can see here is if x equals negative 1. Here and here, if x equals negative 1, then c is going to disappear and b is going to disappear, allowing me to solve for a. So let x equal negative 1. Here, negative 1 squared is 1. 1 times 5 is 5. Negative 12 times negative 1 is positive 12. 12 plus 5 is 17. 17 plus 1 is 18. Here, negative 1 minus 2 is negative 3. Negative 3 squared is 9. 9 times a is 9a. And then negative 1 plus 1 is 0. 0 times that means b is gone. Negative 1 plus 1 is 0. 0 times c means that c is gone. So we now just need to solve this equation here by dividing by 9 so that a is equal to 2. Now the dilemma at this point is there are no more convenient values. We've already used x equals 2, we've already used x equals negative 1, but there's one more value that we have not solved for. b. So if you're out of convenient values for x, remember you can let x equal whatever you want. You can let x equal 10, you can let x equal negative 40, it doesn't matter what x equals. I chose convenient values for x that would cancel off parts of the equation. But we're out of convenient values, so at this point what you would need to do is just choose any random value for x. So I'm going to let x equal 0. It's a really easy value to use. That's not going to cause any pieces of the equation to disappear, so that's not going to help me solve for b. But I also now know that a is equal to 2 and c is equal to negative 1. So I'm going to plug those in as well at this point. If you're not choosing a convenient value, if you're just choosing a random value, you also need to plug in anything that you solved for up until that point. So I'm going to plug all three of these into this equation, leaving b as the only unknown at that point. So if x is equal to 0, then 0 squared minus 12 times 0 plus 1 is just 1. And then here 0 minus 2 is negative 2. Negative 2 squared is 4. And then 4 times a really means 4 times 2. So 4 times 2 is 8. And then here, if x is 0, 0 plus 1 is 1. 0 minus 2 is negative 2. Negative 2 times 1 is negative 2. And then negative 2 times b is negative 2b. And then here, if x is 0, 0 plus 1 is 1. And then c is negative 1. 1 times negative 1 is negative 1. So we combine some like terms here. 8 and negative 1 combine to 7. Now you subtract 7 and divide by negative 2. So b is equal to 3. And now we have all three of the values that we needed to complete the partial fractions. Because remember, here all we had were the form of the partial fractions. We actually need to now write the partial fractions with the particular values of a, b, and c. So a is equal to 2, so it was 2 over x plus 1. And then b is 3, so it's 3 over x minus 2. And then c is negative 1, so negative 1 over x minus 2 squared. And it won't get much more complicated than this when you're trying to find the actual partial fractions. Finding the form of the partial fractions, like we did in Learning Target 1, you're going to have some pretty weird looking expressions to start with, but all you're finding is the form of the partial fraction, which wasn't that complicated. If you're actually finding the partial fraction decomposition, it won't get any more complicated than these two examples that we've worked through here.